I'd like to welcome Anand Pillay from University of Notre Dame to the Colchin Seminar, and he'll speak to us today on interpretations and differential Galois theory.
Yeah, okay, thank you. So this is something with Moshe Kaminsky. He spoke about it in this seminar, January. Okay, maybe January, but this is both a correct version and an extension. So there was a mistake. It's a bit complicated history, but I got involved with it just to. It was very nice mathematics, but I mean both to correct things and extend. And somehow implicit here is some kind of model theoretic account of the Tannakian formalism, but in some more general situations doesn't apply. Okay, so it's about strongly normal extensions. Anyway, I'm talking at experts. I will treat it as I'm talking about. So I'm going to try to be efficient. Okay, I'm not going to be too motivating. I'm going to be efficient. If nobody minds. Yeah. So it's a business. The second talk will be a little bit of a different. The second talk will be more leisurely, but this is like a business talk. Okay, so.
Where you tie?
Pardon? Okay, so it's about the model theory is elementary model theory, but it's about interpretations. I'm sorry, I talked about this too in Korea, but this will be a little bit different. So apologies to for these Alf and Sebastian. So it was the same topic, but a little bit different. So business, right? So the data. We're talking about differential Galois extensions. In fact, strongly normal extensions, but you could think about Picard-Versio if you want. And this is related to some work that Alexei did and a few other people did. So data. K differential, characteristic 0. K a differential field. K 0. I'll take U to be a K. This is contained in U, a big model of differentially closed fields K is 0. Yeah, I said that the model theory is elementary, but it involves the notion of interpretation. I don't know who knows what an interpretation is. I may not even define what an interpretation is. I may not even define it. I'll see how it goes. But the key notion is, but it's an elementary notion of logic. It's interpreting instruction. I'll say a few words about this. So K, these differential closed fields. C is constants, right? C is the constants. I'll write here curly C, but it may not always be curly. CK constants of K. Okay. Now we have G, connected algebraic group over the constants. Okay. And D log G, boom, equals A. So A is going to be, or little A will be a point in the Lie algebra of G. A K point of the Lie algebra. This will be a log differential equation on G over K. So log differential equation on G over K in the sense of Colchin. Okay. Now, if you want to be more concrete, you take G to be GLN. And then in this case, D log, I'll say Z. So Z will be an indeterminate. So the unknown is an indeterminate ranging over G. Okay? The unknown is indeterminate of GLN, so it's an n by n matrix of unknowns. Is just dz z to the minus 1. Yeah? In the standard, right? And in fact, the same is true. So this is the derivative, right? D is the derivation, and so the equation you rewrite as dz equals az, and this is an equation. This is precisely the equation for a fundamental system of solutions of the corresponding equals the equation, the differential equation for a fundamental system of solutions of the corresponding dy equals ay, where y is now a visual, and when you do it on GLN, you're asking for a fundamental system of solutions, right? Okay, so this is all known, everybody, okay? Now, in fact, this log derivative stuff is that also you can write the d log on G. You can also write as dz z to the minus 1. You can also write it like that, where this is computed in the tangent bundle of G. This dz is a point above z in the tangent space. You've got a natural embedding of G in the tangent bundle. Okay, and that's the z, and this multiplication is in the tangent bundle. And this and the image is going to be the Lie algebra, which is the fibre above 0. Okay? So this is the context, these are the objects I'm dealing with. Okay? Any questions? Now a strongly normal extension, so if you want to think about simply GLN, and explicitly, this is multiplication, this is an n by n matrix, multiplication matrices. Okay, so if you don't like algebra, but the point is this deals with, here we deal with arbitrary algebraic groups like abelian varieties, and the Janochian theory is not written down, it's not worked out in that nonlinear context. So, okay, so this is why doing the strongly normal case is, shows the power of model theory in some sense. Okay, a strongly normal definition. A strongly normal extension of K, so this equation I'll write like, I'll call the equation star. Extension of K for the equation star is some L equals K, G, where G is a solution, in a differentially closed field, solution of an equation, such that the constant of L is the constant of K. This is Colchin definition. Right? With the same constants. Now, if you think about it, I mean, the solution space, I mean, kernel of D log G is just the constant points of G. Okay? And this D log is a cross homomorphism. So a solution is a coset of GC. So the solution space is what we call a monotonically internal to the constants. It's expression, we call it internality. So the solution is controlled by the constants, but maybe needing additional parameters to see. Okay? And now this means model theoretically, i.e. it means that the type of G over K is weakly orthogonal in a strong sense to the constants, which means this has a unique, it extends to a unique type. That's the meaning. The meaning of this, the same constants, means that the type of G over K, so when you add G, you don't add new constants. And this actually implies that the type of G over K implies the type of G over KC. This has a unique extension. Type of G over K and type of C over K are weakly orthogonal in a sense of stability theory in a strong sense. Okay, this is the meaning of this. The definable closure of KG intersection C is just CK. All would mean the same thing. They all mean the same meaning. Okay, so it's about really. So the difference, but okay, that's it. Now when CK. Okay, now when CK is algebraically closed, you can always find a strongly normal such extension. You simply take a solution, choose a solution G in the prime model. K diff is the differential closure of K in the prime model over K, and then you're happy. Yeah, merely equals. Has no new constants. Because in the prime model, the constants are just the algebraic closure of CK, but that's already algebraically closed. So, okay? But when CK is not algebraically closed, right? Can't always do it. This whole thing is about the difference between definable closure and algebraic closure, model theoretically. So it's a bit subtle. Can't always do it. And I thought this was a sort of a little bit uninteresting part of the theory, but I mean, it turns out there were some results proved, and I think I saw something of Alexei and a couple of other, Gorchinsky, Gillet, and 2012, I should have approved this actually. In fact, I should have approved this like this, but I couldn't do it, and then because it seemed like an emitting types thing. No, I didn't give the result yet, but there was some results around, and then Moshe somehow had an idea and did so. I'm not really sure. Yeah, I guess one thing is that if you have such an equation, and if you can find a small normal extension, you can realise such a solution without new constants, then the Galois group, which is an algebraic group over the constants, has the structure of an algebraic group over CK. Which means that's just one of the consequences. So the Galois group has a real, for example, if CK is reals, the Galois group is an algebraic group over the constants, has a real structure, has the structure of an algebraic group over the reals. Okay, this is one consequence that the invariants of the equation can be defined over the CK. This is a conclusion of it, whatever that means, and various other invariants, characters and things like this. Okay.
How could you repeat the statement about the reals in more detail?
No, I'm just saying that if you have anyway, what is the meaning of having a strongly normal extension of the equation? Yeah. Well, one consequence is the Galois group, the equation, has a structure, has a CK structure, has a structure of an algebraic group over CK. Well, the face of it is an algebraic group over the constants. Over algebraic closure CK. I mean, the Galois group of the equation as a constant algebraic group is naturally algebraic over the constants, over the algebraic closure of CK. But having a Picard-Versio extension, I think, is probably equivalent to that having a CK structure. That's all I mean. And I'm just taking from a CK was reals. Okay.
If CK is reals, there are counterexamples.
Yeah, they're counterexamples. Okay. So this is the data. Okay. Now theorems.
Anand?
Yes.
Culture proved the fundamental theorem of Galois theorem without assuming constants of the ground field algebra.
Yeah, I don't know. Maybe, yeah. Okay.
Yeah.
Okay. No, I mean, there are.
So that gives you hope, at least. One hope. I mean, one did.
Anyway, and also KG also uniqueness. KG is unique. The Galois, when CK algebraic closed, you can find such a strong normal extension. Moreover, it's unique over K makes unique over K as a differential field. Okay, this is the uniqueness. And when CK is algebraically closed, there is a strongly normal extension. Moreover, it is unique. There's existence and uniqueness. It's unique as a differential up to I over K as a differential field. Okay. So theorems, a few theorems. One, if CK is existentially closed in K as a field. So CK is existentially closed means simply any constructible set defined over K, constructed in the sense of different Boolean combination algebraic varieties, defined over K with a K point has a CK point. Sorry, any one defined over CK. Any algebraic variety defined over CK with a K point has a CK point. And I allow myself not just affine any algebraic variety. Extension closed model theory, we know what it means. Any formula, any quantified free formula in the language of fields with a solution in K as a quantified formula over CK with a solution here, a solution here. This implies, of course, now CK is always relatively algebraically closed in K, always. So this, the EC is stronger than C being relatively algebraically closed. Okay? Then, there is a strong normal extension for the equation stuff. Okay? There exists one. And this was proved in a paper of Alexei and Gorchinsky and Gillet, okay, seeing that theorem there, also generalized to the parametrized theory. And there are other things about T extensions. I don't know what T extensions are. You can tell me at some point what the rest of the paper is. I don't know what it is about. So this was, but that was for the PV context, for linear context. Here we're doing it in the general strongly normal context. That's numero uno, right? Number two, suppose CK is, these are all EC and K, and CK has shared property F. The shared property F is the property that some model theorists call algebraically bound. I forget what they call it. So anyway, the property is that, I'll just say it, I don't want to write it down. CK, the field CK property F means for a field, means it has exactly, it has only finite extensions of degree n for every n. It has finite extensions of degree n for every n. Okay? Is that okay? No, I don't want to write it down. It has, the property F means of a field F, so F is both the field and the property. You don't mind? Okay with this, Russell?
So far.
So it is algebraically bounded, that's the same thing, isn't it?
Yeah, I don't know. So the condition is that it's just a word. It's not rocket science. It's only a word. Don't get it. Don't worry about too much. It's only a word. It's just a word. It's not. They're different words for the. It's just words. So it means that F has finitely many extensions of degree n for every n. Okay? Shall I write it down?
It's on tape.
F has 5 extensions of degree n. For example, the reals, the p-adics. And I think is it algebraically bounded is the same thing? Or has small Galois group? It means the absolute Galois group has finitely many open subgroups of index n for every n.
Yeah.
It's the same thing. It's about the condition of the Galois group. Yeah? Sayre's property, F, right? Then, there is a strongly normal extension, L of K, for the equation star, such that CK is also extensionally closed in L. So the constraints on the constraints on the nature of PV extension. So, for example, it means that suppose, for example, CK was a real closed field, and K was a formally real field containing it, then you can choose L to be formally real also. Okay, I don't know what the meaning, what these implications are, and this should have some implications for, I think, for Michael Singer's theory. Well, Michael Singer's theory, I mean, is first order. There's a Singer first order theory called CODF, with his thesis, Michael's thesis, CODF, closed ordered differential fields. It's the analogue of differential closed for ordered fields. And this should have some consequence. So this is an NIP theory. It's, but there's no prime models, but it should have some meaning for that I didn't sort out yet. So this should have consequences. And plus other stuff. So this result, other stuff around uniqueness. There's other results we have. Like there's a paper. It's on archive. It's called Interpretation of Differential Extension. The paper with Moshe. It's on archive. You can look up for the details there. The other results. There are several other which are new results that are not actually contained in these other papers. But this existence thing was for the case of the reals of the p-adics was proved by Heito and Crespo and Vanderput.
For Picabes.
Sorry?
For Picabes.
For Picabes SEO case.
Yeah.
They proved it. It was first claimed in the paper with Heito and Crespo and Elżbieta Sowa, but it didn't work. Although it was never they knew it didn't. I mean, Matthias Aschenberg told them the proof didn't work, and I think they should have. I saw Heito recently recommended they publish a correction somewhere. So but the correct thing was with Vanderput, and this involves the Holton-Archian, involves using the Holton-Archian theory. Okay, but there's more results too. Let me say a result, for example. Just assuming just assuming CK, EC, and K, you cannot generally get this condition here to find L, but you can do it after replacing CK by an elementary extension. You can, in some suitable form, with a suitable statement, this 2 remains true without property F after moving from CK to a proper elementary extension. Okay? So, a uniqueness, again, doesn't use property F. If you have, for example, CK, EC, and K, take 2 strongly normal extensions, L of K, which have this property here. They're both EC. If they're both commonly embeddable into another field L prime, in which CK is EC, then there's a unique over K up to isomorphism as differential fields. There's a uniqueness statement also without using, not existence, uniqueness without using the property. Okay, so I want to try and say something about these proof. Okay. So as I said, model closure is the difference between definable closure and algebraic closure. It is good proof. So let me say something about this proof. I think in Korea I only talked about one, but the proof depends. So there's a certain objects or there's a certain characters. Now when I say character, I don't mean like mathematical character. I mean like a person, like people, like in a story. You know. So character won't be a map to an obligative group. It'll be like a person. Like an idiot, for example. What's his name? Who was the idiot? Dostoevsky. Raskolnikov. So who was the idiot in? What? Who was the idiot? Who was the main character in Idiot? What?
Smerchikov?
I don't know. Anyway, it could be think of the character as him. Okay. So here are some characters. Again, I mean in a sense. Okay, Russell? Yeah. So, characters, so objects involved in proof. And maybe these are maybe as interesting as the proof itself, the objects, all the people around are interesting. So, some of these I'll just write down the symbols, and sometimes I may describe what the symbols refer to, okay? Without writing it down. So Y equals a solution set of star, the equation star, right, d log, so Born equals A, in U, in the big differentially closed field, i.e. so Y is a subset by definition of G, because the equation is on the algebraic group G. So it's a collection of solutions in G in the sense of the differentially closed field which satisfy the equation. Okay? Good. That's one thing. Now, I will write M to be C, Y, the structure, the first order structure, with two sorts, constants, solution set, with all induced structure coming from the differentially closed field with parameters from K. Structure from U plus times with parameters from K. So you take, what's this? I'm looking at all, I'm adding relations if you want, for all subsets of C cross C cross C cross Y cross Y cross Y, which are definable in U over K. Or if you want, I'm looking at differential algebraic subvarieties of U cross of C cross C cross C cross U cross Y cross Y cross Y. Yeah? Different varieties over K, and adding a predicate on this for that. This is a structure. Okay, it's simply the... And I'll let T tilde be the first order theory of that. The question is, what is there a fundamental... Well, what language? The language, if you want, for now, of differential algebra, of these predicates for these varieties, but later I'll be precise about the language. T will be ACF. I write like this. What this means is, this is motion notation, which is bad notation, but what I mean is algebraically closed fields with constants in the sense of logic for elements of the CK. It's algebraically closed fields. It's just algebraically closed first order theory with constant symbols for elements of CK together with a diagram of CK. So actually a standard model is just C plus times A, which just the constants, with names elements of C. Then also ACFK. I've got no name for it. This is the algebraic closed fields with names for K. Standard model would be U plus times A and K. Okay, this is my algebraic closed fields with the so I'll just call it ACFK, I'll call this T. F from y to, say, constant to some power d will be a function definable in u plus times with a derivation over k such that what? Such that for each b y, the type of b over k together with the constants is implied by the type of b over k together with f of b. This is a standard model theory thing. You've got b. I work in differentially closed fields with names for k, elements of k. You have a definable set C. I'm looking at canonical base of type B over C. Yeah, this is definable. This is a definable set. We're in a stable environment. Yeah, type B over C is definable. That definition has a canonical base. Yeah. Boom, 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 boom. And this is a definable closure of B. And the type B over this person implies type B over everything. Okay? This is. But why is there such a function? Why is this done uniformly by a function? You have to prove it, and I'll mention it later. But there is such a function. Key function, okay? Now this action will be definable, is from y to c definable over k. So in fact, it's definable in this structure here, because I allow all things definable over k from the ambient differentially closed field. So it's actually definable in M. It's definable in M. In the structure, without parameters. O will be the image of F. Now it's rather interesting. You have this M structure. We have M, right? We have M. It doesn't matter. I've got. If you want, I've got M, or I've got DCF, right? I've got U. I've got the constants. I've got this function y, f, to the constants. Okay, and the image will be definable in DCF0 in the constants over k. But therefore, it's definable in this algebraically closed field over the constants. Because C is just, with this, all its induced structure, it's just an algebraically closed field. And the only trace on C of K is the constants of K. So in fact, OF, so what this means is, O is definable, zero definable in T, in constants plus time, without the derivation. There's no derivation, it's trivial, and the names for. That's an important object, an important fact. Now omega will be a
It's Halloween.
what?
It's Halloween.
What?
It is Halloween.
Maybe there's some more should go on to other lecture. Should we adjourn this lecture to see what's going on?
That'd be too scary.
Will be an interpretation, a certain interpretation of M of T tilde in ACFK. T tilde ACFK. Okay, now I should say what interpretation means in a second. By the way, as I said before, this means that definable closure of KB intersection C equals constants of K adjoining A or something, that's what it means. FB. And this is just KB itself. This is just KB. So it means the constants of CKB of KB are just the constants of K adjoin FB. Now, on interpretation of T tilde, I'll mention interpretation in a second. To interpret a theory, another theory is to sort of, one theory is in a certain language, another different language. You simply find a copy of this theory, the other theory. Did you do interpretations?
I skipped that.
You skipped interpretation, the most important thing in the world.
I know.
Interpretation. You skip
It comes very
interpretation.
early in my book, but I had to skip it because of the audience.
I skipped it too.
I mean, because this paper is what I call about the yoga of interpretations.
So that's the yoga.
It's the yoga of interpretations. It's the yoga of interpretations. Okay, so I'll say about the second interpretations. Okay, but this is the analogue of this is the forgetful interpretation.
It's in the book.
It's forgetful. It's the analogue of the forgetful functor
Groups.
in this Narkian theory. It's analogue of the forgetful functor. In this Narkian theory, given the differential equation, you have a Tanarkian category of vector spaces over K equipped with connection. Okay, and equipped with connection. And the forgetful functor forgets the connection. Connection is the differential, forgets the connection. Okay, so this is essentially the forgetful functor from the Tanarkian theory. For each element A, sorry, I can't. For each element A in O, in the image of F, we have another interpretation. The interpretation I'll call omega sub A of T tilde, in fact M, the structure M, in C plus times D, say D and CK, with parameter, an interpretation of this, in this canonical interpretation with parameter, defined with parameter A, with interpretation used parameter A. This is omega A is the analogue of the fiber functors. In Tanarkian category, in Tanarkian context, in Tanarkian treatment. So I'll say interpretation in a second, right? So the interpretations replace, these interpretations are like the functors from one category to another category. From a Tanarkian category of vector spaces with connections to vector spaces. Okay. In fact, in TA, it's interpretation of T tilde in TA. TA is T with a name for A, additional parameter. Now G and G plus will be the Galois groupoids, will be the G plus, will be the extended to G plus Galois groupoid attached to the equation. So I don't know, do we know what, I mean, this is, was this the enculture, this Galois groupoid of a strongly normal extent of was this the enculture do the Galois groupoid?
He didn't never mention the groupoid. He did the Galois group.
Yeah, so the point is the Galois group, we know that there's choices for the Galois group. You know, you choose, there's a choice based on choice of solution, whatever it is. Okay, you can canonical fashion, and this is the actual natural object. Is also with It's an archimetry. So what do I mean here? Galois groupoid. So I'm going to say something. Before saying this, I want to say ought. An automorphism group. This is the Galois group as an automorphism group. It's the permutations of the solution set, all right, preserving all differential relations and fixing point by point K and the constants in the big saturated model, in the big model. So it's like Colchin's Galois group in the big model. It's not the, Colchin, there's a group in the big model and a Galois group down, right? So it's the big Galois group. This is ought, it's automorphisms, okay? It's automorphic, it's the binding group in model 3. Y is internal to C. After you name a point of Y, it's in bijection with GC. And all automorphisms induce, if you want, all permutations of this, induced by automorphisms of the differential field, U, which fix K, C point by point. Yes? Okay. So again, I have G and G plus. These groupoids. What is objects of G is just O. So G is definable. G is definable, zero definable groupoid in C with names for K, right? In T, if you want. Theory of C with names for CK. G plus equals G, objects of G, the objects of G, of the groupoid G are just the O. Oops, O, right? Objects of G plus is O, objects of G, together with a new symbol plus. Okay? Maybe I'll say some words about this because I may not. Yeah. So explanation, okay? Explanation.
What plus is?
It's another. What is this stuff? Explanation is right. So you have B, right? Given B in Y. So B is so Y, as I said, is a coset of the constant points of G. Right. So after naming B, you get a bijection of the constant points. I call it HB. Is Y to GC, just as Y goes to B to the, I think it's right. Yeah. So, after naming, here is my Y and my C, after naming a point B, I get this natural bijection of Y, and this exactly is an interpretation of Y in here. So okay, this is okay. So forget the this actually is okay. This gives rise to the interpretation of M in C, using the parameter A, which is f of B. I don't need this for now. Look at this, HB. Okay. Yeah. Now the morphisms. Now the morphisms for A1, A2, and O. The morphisms. I do it like this. Yeah. A1, A2, and O. The morphisms between A1 and A2 is the set of HB2, circle HB1, where f of B2 minus 1, yeah? F of B2 equals A2, f of B1 equals A1. Now what does this mean? It's the Yeah. So HB1 to the minus 1 will be a bijection between GC and Y. Composed with that, we get another map. So this is something, right? Anyway, so morphism, right? Morphism A and A, I'll call HA. This is the Galois group. This is the usual Galois group, depending on the choice of B. It's defined over A. Galois group. The HA is a subset of G of C, defined over an algebraic subgroup, defined over CK together with A. Okay, so HA, these we see here the Galois groups as, so for the objects O, the morphism A to A and O is just the Galois group HA, H, depending on the choice of the solution B. If you have A1 and A2, the morphism from here to here will be a PHS for the Galois, for HA1 and for HA2. This you see the, right, this is a lecture of isomorphisms between something, okay? And what about plus? Can I come later to the rest of to the plus? Can I discuss the plus later? I mean, the point is that the morphism plus plus will be the intrinsic Galois group. I was saying defined by Katz or something, more or less. The intrinsic Galois group is going to be an algebraic subgroup of G. It'll be a definable subgroup. I'll call H plus. It's a definable subgroup over K, differential algebraic subgroup of G. It's the intrinsic Galois group. It means the Galois group, which is not a group of the constants, but it's a definable subgroup. It's the Katz. I mean, it's a risky closure. It's the group that Katz defines. Do we know the Katz paper on? It's what? It's an algebraic group over. Okay. Let me just leave things for. Right, can I come back to some of these objects later?
Yeah.
Yes.
Yes.
Okay. Now the point is that there's a. If you look at all these Galois groups, right? There's maybe I'll say we'll say something now. Right? We take. We take Y and we take C. Yeah? And we have this automorphism group of Y over C. Yeah? Aut, which is a group of permutations. And the point is, this is a definable group, as well as the action. And the definition that the action may require additional parameters. And the choice of the parameters is reflected in the group point. Yes? And there's one choice of doing it which is intrinsic, which is without parameters. I call this the intrinsic group. The other, and this is the Katz, this is essentially a group introduced by Katz in one of his things. The usual group, which Daniel Bertrand calls everybody's Galois group, is the group in the constants. But on the face of it, unless the group is commutative, this depends on this needs a choice of parameter, which gives the group after conjugacy.
Yeah.
When you package all this together in a canonical fashion, you get the group point. This is the idea. Okay, the plus. Okay, so what is happening? Let's give a little bit of. Let's define the plus. Let's define the plus group. Okay, the intrinsic group. Okay. And let sigma be in over KC. look at sigma b. Now y is of course living inside GU. Look at sigma b times b to the minus 1 in the sense of the group G. Right, so b is here, sigma b is also somewhere here. Look at sigma b to the minus 1. It's independent of the choice. It's independent of the choice of b. It's independent of choice of b. Okay, this way, the other way around, no. This way around it isn't independent of choice of b. And the map, taking sigma to sigma b to the minus 1, is an isomorphism of groups between ought y over kc as a group and some definable differential algebraic. Define me the differentially closed field. Differential algebraic and some differential algebraic subgroup H plus of G U defined over K. I'll just say the action of this automorphism group on Y is also, this isomorphism produces an isomorphism of actions between the action of this group on Y and the action of H plus on Y by left multiplication in the group G. Now this is the intrinsic, it's a differential algebraic group. It's isomorphic to a group of the constant, but after naming the parameter.
Yeah, it should be.
So it's a form.
Yeah.
It's a certain form of a group over the constants, right? This is H plus. It's a risky closure.
Oh, that's cat.
It's a risky closure, it's Katz's group, which is more or less automorphism of the functor omega A, of the fiber functor. So H. So if you want to look compared to the Tanakian sort of theory, so Tanakian, the kind of analogues is like H plus is risky closure. Is risky closure equals the automorphism group of the functor O. HA of omega. H is the automorphism group HA of omega. Okay? This is the.
Omega is the forgetful function.
Sorry?
Omega is the forgetful function.
Yeah. So the automorphism group, that forgetful functor, is more or less, in the sense of the Tanakian theory, is more or less the Zariski closure of H plus, which is an algebraic group over K. If you look at Daniel Bertrand's, Daniel's, he wrote a very nice kind of review, I think in AMS Notices, of Andy Magid's book. And he just gives a very quick summary of the delirium.
Bulletin.
Bulletin.
Yeah.
Bulletin AMS.
Yeah,
What did I say?
You said a notice.
I meant bulletin. Very nice. And he talks about all these objects there. They all appear there, these objects. But the thing is, I'm working a bit differently. I'm working really in the big differentially closed field. These objects, they come from somewhere, not necessarily in K or whatever. They're objects and somewhere. And that's important for this point of view. So it's not exactly a 1-1 correspondence with Tanakian. This is H plus, okay? We also have the other way around. We also have sigma, and this, again, this is independent of the choice of the solution B. It's important. You just compute. This is independent by the Galois. B to the minus 1 sigma to no. Yes, sigma to b to the minus 1 sigma b. Okay. Oh. This gives an embedding, an isomorphism of what y over kc with an algebraic subgroup of G, I call it HA, of GC defined over what? Over A, which is f of B. Okay? And the action, so this is a group, the action, right? So the action, the natural action on Y of this group, induced by the automorphism, right, needs the parameter B to be defined. The action of Y needs parameter B. So the group is defined over A, which is f of, right? A was the image of B under F. And needs action of on Y needs B. That's it. So really you have plus, you have all these A's, 1, A2, morphism plus plus is H plus, morphism A1, A1 is HA1, etc. And you've got these connecting things. And the total groupoid, in fact, the total, so it's a definable groupoid. The objects are definable, uniformly definable. The collection of the groups and the group-like things are defined uniformly. So there's no definable groupoid. This part of the groupoid G is definable just in algebraically closed fields with names for CK. If I add that, I need to work in T tilde, where you allow the Y, okay? This is really, that's it. Now, it's now 1:30. Jesus. Days of Chris, I didn't even find interpretations. How long do I have for this? Another 15 minutes or so?
Depends on when you want to start your next talk.
Yeah, 5 and 2.
So, to prove one, okay, so I've used the object. To prove one, we need a small part of this picture. Just omega and the, so interpretation. Can someone else define interpretation? Philip, can you define interpretation?
Right now?
Now.
We can postpone.
Postpone to where?
Just like definable.
The ginger man.
It's like the fun.
Yeah, it's just definable in MEQ.
For example, no, it's for example.
Do a very quick example.
Pardon?
Do an example instead of trying to define it.
You know, I've got a structure in sense of logic, so I'm assuming we all know what a first order structure is. If not, then I don't know. I've got to assume something like that. Okay, but that first order structure may contain. I mean, for example, if you take complex field. Now take the family of lines through the origin in two space. Straight line through the origin. Yeah? No, affine lines. Look at the lines. Look at the straight lines, not affine lines in two space. As a collection of with incidence relation, or no, together with what? I don't know what. I want to have. What is natural? Tell me the natural structure for the combinatorial for instance geometry. You have the collection of lines, and you have the points, and you have what do you have? The points and the yeah. You have C2. Consider C2. The set of lines and membership. So, points in C2, collection of all lines. Not just through, let's say any lines. Through the lines, affine lines, right? So it could be straight lines, yeah? And the relation a point here lies on a line here. This lives in this structure. Because that's definable.
Yeah.
This is definable. The collection of all lines is definable. If you think about it, the membership is definable.
Yeah.
So this is interpretable in this structure.
Say
And if
C and R is even easier.
yeah. Now actually a bit more. You can actually recover this structure back from this again. This one is the fundamental theorem projective of geometry or something, right? So in fact these are what we call bi-interpretable. Okay. For example, the constants in an algebraically closed field is interpretable in in differentially closed fields.
Yeah.
Okay? Interpretation. Okay? And the key point here is interpretation omega. So let me say something about 1. So some proof of 1. So 1 uses just omega, F, and H plus. 2 uses everything. 2 uses everything. 2 uses everything. It's more complicated. 1 you omega. So what is omega first? Omega was a forgetful interpretation. I want to interpret. So this is a bit related to something I did some time ago with Kowalski. We have an old paper called Quantify Elimination for Algebraic D groups. I think it was Transactions AMS. And there we show that in differentially closed fields goes to 0, any finite dimensional differential algebraic group viewed as a structure in its own right, which means you equip it with all differential algebraic sets of n-tuples, right? So view it as a structure in its own right, is interpretable in algebraically closed fields. It lives as actually a reduct, it kind of lives as an algebraic group, forgetting sums, risky closed sets. So it's quite amazing. On the face of it, you think this is stronger than algebraic closed fields, but actually it's weaker than algebraic closed fields. I mean, if it happens to be a group in the constants, then it's just a group in the constants, finito, right? That's the algebraic group in the constants. But if it's something else, it's still interpretable, and that's, okay, this is the forgetful function, essentially. So what do? We take Y and C, that's N, two-sorted structure, and for each K definable, this means defined over K. When I write K, I mean defined over K. When I say, I don't mean, some people say mistakenly this to mean definable in K, and it's simply an error, a typing error. Even some of my friends say this, some of my best friends say this, but they're making a mistake. So it's defined over K. K definable set X in, say, Y to the boom boom times C to the boom 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 boom, some Cartesian power. Let Rx be the risky closure in GU cross boom 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 cross U boom boom boom. So Y is a subset of GU, this is a subset of that, takes risky closure. This is an algebraic variety over K. Okay? Just put that in the language. That'll be the language. Add a relation for this. Yeah? So that's my language. Then we have CY is a subset of U, GU. I equip this structure with all these relations. I interpret these relations here just by restriction. Then, numero uno, elementary substructure. And number 2, these relations here are enough to recover all the definable sets I started out with. This is the forgetful interpretation. This is the functor. This is the functor. This is the interpretation. Essentially, the differential algebraic variety is replaced by its risky closure. Okay, this is omega.
So that's kind of weak. Isn't that
Yeah.
weak?
No, so you get, but it's enough information to understand everything about this structure. So this lives in this structure here. The solution of the differential equation actually belongs to algebraic geometry. In a sense, this is omega, right? Good.
So that's only in the finite dimensional setting
Well,
for the group,
yes, you have to, because algebraic closed fields is finite dimensional theory. So to interpret anything there, you like to be finite dimensional. So you cannot hope to do anything. It has to be finite dimensional. But all of these things generalize to this several derivations to the parametrized thing. All relative acid. What about F? What about F? Well, I take Y, my solution space. Yeah? We have H plus. this definable group. Remember, acting